Hello and welcome to Algebra 2 Practice Set 67. In this video, we're going to look at some additional practice problems for our lesson on quadratic and rational inequalities. All right, so we want to solve each inequality and graph the solution set. So we're going to take a look at 7n squared plus 41n plus 30 is less than or equal to 0. So the first thing we want to do here is just change this into an equals, and we want to solve that equation. So we would have 7n squared plus 41n plus 30 is equal to 0. So we could solve this using the quadratic formula. We'll say that n is equal to negative b. In this case, again, this is a, this is b, this is c. So negative b would be negative 41, then plus or minus the square root of, you've got b squared. 41 squared is a pretty big number. It's 1,681. Minus 4 times a is 7, times c is 30. So 4 times 7 we know is 28. 28 times 30 would be 840. So I would have 1,681 minus 840. If I perform that operation, I'll end up with 841. Now, what is the square root of 841? That's going to give me 29. So this will be a 29 here. And then this whole thing is over 2 times a. A is 7, so 2 times 7 is 14. So you'll have two scenarios here. You'll have n is equal to negative 41 plus 29, which would be negative 12 over 14. So negative 12 over 14, which of course each is divisible by 2, so it's negative 6 sevenths. So n equals negative 6 sevenths, or n could also be, you have negative 41 minus 29, which is negative 70 over 14. So negative 70 over 14. And if I divide negative 70 by 14, I get negative 5. So I have n equals negative 6 sevenths, or n equals negative 5. So once I have these two solutions, what do I do with them? Well, let me erase all this, and we're going to take this down to the number line. Remember, these two represent endpoints, or you can think about them as boundary points. They're going to separate the number line into solution regions and non-solution regions. So negative 6 sevenths is going to be between 0 and negative 1. It's going to be pretty close to negative 1, so let's just put it right there. So we'll say this is negative 6 sevenths. And what I'm going to do is I'm going to make a little vertical line there, just to signify that this is going to separate things. And then I'm also going to do that at negative 5. So I'm going to do that here as well. And essentially what your textbook will do, or most teachers will do this as well, you'll just write like a capital letter in, something to say like, hey, this is region A, anything to the left of negative 5. Then between negative 5 and negative 6 sevenths, we'll call this region B. And then anything larger than negative 6 sevenths, we'll say this is region C. Okay. So now what we want to do is we want to identify test points, so any number in the region, plug them into the original inequality and see if they work. If the test point works, that region is part of the solution set. If the test point does not work, then it's not part of the solution set. So let's just pick negative 6 from region A. And if I plugged in a negative 6, what would I get? So negative 6 squared is 36. So you'd have 7 times 36 plus 41 times negative 6 plus 30 is less than or equal to 0. So 7 times 36 is 252. And then 41 times negative 6 is negative 246. So minus 246. And then plus 30. And this is less than or equal to 0. So you can already see that this won't work out, right? This is going to end up being positive. But for the sake of completeness, 252 minus 246 is 6. 6 plus 30 is 36. So you get 36 is less than or equal to 0, which is false. So for region A, you can say this is false. So anything left of negative 5 will not work. Now, anything to the right of negative 5, but less than negative 6 sevenths, that's going to be region B. So from region B, let's just check negative 1. So I'm going to plug in a negative 1 everywhere I see an n. So negative 1 squared is 1. So you'd have 7 times 1, or 7, plus 41 times negative 1 is negative 41. So you might as well say minus 41. Then plus 30, and this is less than or equal to 0. So 7 minus 41 is negative 34. And negative 34 plus 30 is negative 4. So negative 4 is less than or equal to 0. That's true. So this is true. So for region C, let's check 0. So if I plugged in a 0 here and here, basically this would be gone. You'd have 30 is less than or equal to 0. That's false. So anything in region C would be false. So the only values that would work here, because we have a non-strict inequality, your endpoints will work, right? If I plugged in a negative 5 for n in that inequality, I get a true statement. If I plugged in a negative 6/7, I would also get a true statement. So those will be included. So graphically, I can kind of erase all this stuff. I would put a bracket at negative 5, and I would put a bracket at negative 6/7, and I would just shade everything in between. So negative 5 is included, and anything up to and including negative 6/7. So we could also say in interval notation from negative 5, right, with a bracket next to negative 5 because it's included, up to and including negative 6/7, again with that bracket next to negative 6/7 because it's included. Another way we can notate this is with set builder notation. We could say the set of all n such that you'll have n is greater than or equal to negative 5, and n is less than or equal to negative 6/7. All right, so now we're looking at 9p squared plus 18p is greater than negative 5. I would just add 5 to each side of the inequality to get things started. I would have 9p squared plus 18p plus 5 is greater than 0. Okay, again, all I want to do is replace this with equals. And so I'd have 9p squared plus 18p plus 5 equals 0. So to solve this guy, again, I can use my quadratic formula. So I can say that p is equal to the negative of b. b is 18, so negative 18, plus or minus the square root of b squared. 18 squared is 324, minus 4 times a is 9, times c is 5. This is all over 2a is 9, so 2 times 9 is 18. So under the square root symbol, if I do 4 times 9, that's 36. 36 times 5 is 180. So 324 minus 180 is 144. Square root of 144 is 12. So what I end up getting here is that p is equal to what? Negative 18 plus 12. That's going to give me negative 6 over 18. Negative 6 over 18 is negative 1/3. Then or the other scenario is that p is equal to negative 18 minus 12, which is negative 30 over 18. So negative 30 over 18, each is divisible by 6. So that would give me negative 5 over 3. So p equals negative 1/3 or p equals negative 5/3. So let's copy this. And so negative 1/3. So that's going to be between 0 and negative 1. It's going to be about right there. So let's say this is negative 1/3. And then negative 5/3 is between negative 1 and negative 2. So let's say that's about right here. So this is negative 5/3. So again, these are our endpoints or our boundary points. So let's just draw a vertical line here and one here. And let me make that a little better. And so this will be region A, region B, and region C. So again, you want to use just a little test point from each one. So in region A, I can just pick negative 2. I plug in a negative 2 for p in the original inequality. Let's see what we get. Negative 2 squared is 4. 9 times 4 is 36. Plus 18 times negative 2 is negative 36. So 36 plus negative 36 is 0. You get 0 is greater than negative 5, which is true. So this is true. Then for B, region B, I can use negative 1. So negative 1. So negative 1 squared is 1. 1 times 9 is 9. Plus 18 times negative 1 is negative 18. So I might as well just say you have 9 minus 18, which is negative 9. Is this greater than negative 5? No, right? So that's false. So in region B, it would be false. And then in region C, I can use 0. So if I plugged in a 0 for P, this would be gone. I'd have 0 is greater than negative 5, which is true. So this would be true. I have a strict inequality. So negative 5/3 and negative 1/3, those will not be included. So anything to the left of negative 5/3 would work as a solution. So let me graph that with a parenthesis and just shade everything to the left. Then anything to the right of negative 1/3 would work as a solution. So again, let me put a parenthesis and shade everything to the right. So in interval notation, I have a parenthesis, negative infinity, comma, negative 5/3. And it's the union with this other set. We're not including negative 1/3, so I have a parenthesis, comma, infinity, and of course a parenthesis. In set builder notation, we could say the set of all p such that p is less than negative 5/3 or p is greater than negative 1/3. All right, let's take a look at some that involve rational inequalities now. So we start out with 2x plus 3 over x minus 4. This is greater than or equal to 1. So the idea here is to get a single fraction on one side, 0 on the other. So we can easily accomplish this. Let's just subtract 1 away from each side of the inequality. And what we'll have is 2x plus 3 over x minus 4, then minus 1 is greater than or equal to 0. So I will now get a common denominator going. So let me scroll down. And I'll just kind of scooch this over. So I'll multiply this by the quantity x minus 4 over x minus 4. So I will have negative 1 times x, which is negative x, and then negative 1 times negative 4, which is plus 4. So you'll have negative x plus 4 in the numerator. And of course, the denominators here are the same. So I can just combine the numerators. I can say 2x minus x would be x. And then 3 plus 4 would be 7. So this would be x plus 7 over x minus 4, and this is greater than or equal to 0. Now for a rational inequality, it's a little bit different. Once you get to this step here where you have a single fraction on one side and 0 on the other, you want to take your numerator and set it equal to 0. So x plus 7 equals 0. You want to do the same thing with your denominator. So x minus 4 equals 0. So the results here for x will give me the endpoints, right? Or the boundary points where we're going to have the separation between the solution and the non-solution regions. So if I subtract 7 away from each side of this equation, I get x equals negative 7. If I add 4 to each side of this equation, I get x equals 4. Now, there's two things to note here. The first thing is that this guy right here came from the numerator. So if I plugged in a negative 7 for x, negative 7 plus 7 will be 0. 0 divided by whatever's in the denominator, as long as it's not 0, which it won't be, will give me 0. So that would satisfy the inequality. 0 is greater than or equal to 0. 0 is equal to 0, so that works, right? Because this is a non-strict inequality. This is non-strict. So x can be negative 7, so we just want to notate that. But x cannot be 4. If I plugged in a 4 for x, 4 minus 4 is 0. I'd be dividing by 0, and that's not allowed. So we notate this is from the denominator. All right, so we have negative 7, which is right here, and we have 4, which is right here. So I'll just draw a little vertical line there, and then also there. So again, 3 different regions. We'll call this region or interval A, interval B, and then interval C. So just choose a number from interval A. We can just choose negative 8. If I plugged in a negative 8 for x, what would I get? 2 times negative 8 is negative 16. Negative 16 plus 3 is negative 13. Then this would be over. If I plugged in a negative 8 down here, negative 8 minus 4 is negative 12. So you'd have negative 13 over negative 12 is greater than or equal to 1. That's true, right? Because this would end up being 13 twelfths. 13 twelfths is larger than 1. So this is true. Then take something from interval B. 0 is easy to work with. So if I plugged in a 0 for x, 2 times 0 is 0, so you'd have 0 plus 3, or 3, over 0 minus 4, which is negative 4. So you'd have negative 3/4 is greater than or equal to 1. That's false. So this is false. And then in interval C, I can just pick 5. So if I plugged in a 5 for x, what would I get? 2 times 5 is 10. 10 plus 3 is 13. Then this is over 5 minus 4, which is 1. So you'd basically have 13 is greater than or equal to 1, which is true. So this is true. Okay, so I know that -7 works as a solution. Talked about that earlier. This is a non-strict inequality, and this is the one from the numerator. So when I graph this guy, -7, I'm going to use a bracket there because it's included, and I'm going to shade everything to the left. For 4, I know that was my solution from my denominator. That's not going to be included, right? Because that would make my denominator 0. So when I graph this guy, 4 is going to get a parenthesis, and I'm going to shade everything to the right. So that's graphically. If we look at an interval, we would have from -infinity up to and including -7, and then the union with, we'd have not including 4, but anything larger. And of course, in set builder notation, we could say the set of all x such that x is less than or equal to -7, or x is greater than 4. All right, let's take a look at one more. So we have m plus 7 over 3m plus 2, and this is greater than 3. So m plus 7 over 3m plus 2. And I would subtract 3 away from each side, so -3. And again, this is greater than 0. So to get a common denominator going, I would just multiply this by 3m plus 2 over 3m plus 2. Let me kind of slide this down a little bit. I'll do 3m plus 2 over 3m plus 2. -3 times 3m is -9m. And then -3 times 2 would be -6. So I would have -9m plus m, that's -8m. I would have -6 plus 7, that's 1. So essentially what I'll have here is -8m plus 1 over 3m plus 2, and this is greater than 0. Okay, so now all I want to do is very, very simple. I want to set the numerator equal to 0, so -8m plus 1 equal to 0, and I want to set my denominator equal to 0. So 3m plus 2 is equal to 0. Subtract 1 away from each side of the equation here. I'll get -8m is equal to -1. I'll divide each side of the equation by -8, and I'll get m is equal to 1/8. Then over here, I subtract 2 away from each side of the equation. I get 3m is equal to -2. I divide both sides by 3, and I get that m is equal to -2/3. Now, we're dealing with a strict inequality, so neither one of these is going to work as a solution. So I'm going to take m equals 1/8 and m equals -2/3 and bring them down here. So let me kind of scooch this down a little bit. So 1/8, let's just say that's about right here. So let's just say this is 1/8. And -2/3, let's just say that's about right here. So this is -2/3. And it doesn't need to be perfect. We're just doing this for a visual representation. So I'm going to make a little vertical bar there and there. This is region A, B, and C. So from region A, let's just pick -1, and let's plug it in here into the original inequality and see what we get. So -1 plus 7 would be 6 over 3 times -1 is -3. -3 plus 2 is -1. So 6 over -1 is -6. -6 is not greater than 3, so that's false. So this is false. In region B, I can choose 0. If I plugged in a 0 for m, I would have 7 over 2. So 7/2 is greater than 3. 7 divided by 2 is 3.5, so that's true. So this would be true. And then for region C, I can choose 1. So if I plugged in a 1 for m, I would have 1 plus 7, which is 8, over 3 times 1, which is 3, plus 2, which is 5. So I'd have 8/5 is greater than 3, which is false. 8 divided by 5 in decimal form is 1.6. So this would be false. So we know that -2/3 and 1/8, neither one of those would work as a solution. So we're going to use a parenthesis to graph in each case. And because it's going to be true in interval B, I'm going to put a parenthesis facing to the right here and a parenthesis facing to the left here. And essentially, I'm just going to shade everything in between. So anything that's larger than -2/3 up to but not including 1/8. So in interval notation, I'll put a parenthesis next to -2/3, then comma 1/8, and a parenthesis. And then in set builder notation, I'll say the set of all m such that m is going to be greater than -2/3 and less than 1/8.